Should we start? Okay, so this is the second session. We'll continue from where we were last time. Maybe I'll just do a quick reminder. This was also on the homework that I sent you to whoever got a chance to look at it. But we ended the previous session with an example. We actually defined Zn, okay, and actually Zn is, we defined it as the set 0, 1, right, where these are all the classes, okay? So it's actually the set of classes 0 to n minus 1, okay?
What is the definition for each class? Like for n minus 1, what is the definition?
So the class,
n.
m equals to m plus n, okay? Where n is like the subgroup generated by multiples of n. So this is like, this would be like minus n, 0, n. Okay. And so we defined it with the plus operation, but the plus operation we said that works a little bit differently than the normal plus operation, because you need to define what it means actually to add two of these sets, right? Because they're just like their equivalence classes are just sets, right? And we said that the plus operation is defined in this way. So this is a special plus operation, and it's actually equal to the class, which is the class where we add A and B. Okay, and this is the normal add, right? So this is the standard add. Oops. And this is the definition of the new add. Okay. So under this definition, this is a group. Okay, and you can check it. Okay, and this group is called Zn. Okay, and actually this group also we also showed that, or maybe we didn't explicitly show it, but we developed it from the congruence, right? We said that we started with the equivalence relation of A equals B mod n, right? We base everything on this this equivalence relation, right, of A and B, if you remember, right?
Yeah, but it's not exactly B mod n, right? B mod n is
It's A equals, when you write something like this, it means that A and B are equal when they are in modulo n.
But you mean A mod n equals B mod n?
No, not necessarily. I just mean that when you say mod n, it's like we could have written it, but it's just a long way to write it. Okay? That's what it means.
Mm-hmm.
That they're equivalents in that they are equal in the world of mod n. That's what mod n means. Okay? Mod n is not, it's not an operator that you're like, don't think of it as an operator. Okay? Just think of it as, it's like, this is how we define this this equivalence, okay, or congruence. Okay. Now, right? So actually Zn, right, we could always think about it, and this is how we use it in practice, right, is that we really take the integers, right, and this is a bit of abuse of notation, right, but if we take the integers mod n, okay, and this actually will give us like the set 0, 1 to n minus 1, right? And then we treat mod n as an operator, right? We get Zn. Right?
Yes.
Okay, so it's like a nuance, but really this is what we mean. When we do this is what we mean. Okay, so Zn is actually, we mean the partition of the set Zn according to this congruence relation.
Is it easier to like treat mod n as you
That's
used
fine.
to treat mod n and write like the definition here?
In practice, it's fine, right? But you always need to remember that it came from this. That's important, okay? So now,
also in a lot of academic papers, that is the way of addressing the modern syntax.
yeah, and you'll see, I mean, hopefully today we'll see how far we get and where we decide to stop, but we'll see how this relates, how we can use this to create like an isometry. So there's another way of looking at this, which is isometric to this. And hopefully we'll get to it by the end of this session, but I don't know, we'll see. Maybe not. Maybe we'll do the next session. Okay, so now just a few additional properties that and this should be quick, okay? It's just a little bit of counting now, okay? So first of all, we call a group finite if its order is finite, okay? And the order we use the absolute value notation, okay? And that's the order of G, right? This is basically the number of the elements in G, okay? In the group G or the set of the group G. So if this is, for example, if this is smaller than infinity, and this is always obviously a positive number, right? If this is smaller than infinity, then we call this a finite group. Okay? Otherwise, it's an infinite group. And that's one.
By order, you mean the number of
cardinality, number of elements in G. Yeah. So like the group that we had before had n elements.
Yes.
So the order would be n. Okay? Okay, so when we write something like this, this means that H is a subgroup of G. Okay? And if H is a subgroup of G, it needs to do two things. Okay? One, it needs to be a subset of G. And two, it needs to be a group on its own with relation to, I'll write it like, which a plus of G. Okay? So with the same operation of G. Okay? If I have a subset of G that is a group with relation to the same operation of G, this is called a subgroup. Okay? This is a subgroup.
So
Now,
all the even numbers.
Oh, if we want examples, yeah. We can look at, say if Z is the group, then we can say that, right, all the even ones is Z2, right? That's a subgroup. Okay?
With the same plus operator.
Same plus operator. It has to be the same plus operator. Okay? Okay, and this would mean actually that now I'm abusing what I did before. So this is actually, I'm actually referring to like, or, you know, or maybe I'll just say even integers, okay? And width plus mod 2, okay? Mod is an operator. Sorry?
With plus.
With plus.
Plus.
Sorry, you are right. Yeah, still need to wake up this morning.
Mm-hmm.
Even integers with plus, so it's actually not Z2, right?
2 times 6.
That's true. That's how you write it. It's 2Z. That's correct. Okay. Now, when we look at subgroups, it's also important to note that that if we take, for example, right, we'll take like A in G, right, and then we'll form a group from it by taking all the powers of A or whatever, and we call it powers, right? And powers is for multiplication, but whatever, we understand. So if we take all the powers of A, this creates a cyclic group, right? So this would be the cyclic subgroup, or let's call it SG of G generated by A. Okay, and it's pretty standard. And obviously we can again talk about the order of A, okay? And if A is finite, then the subgroup is finite. Okay, now...
How can it be finite if we define it as like the addition of A to itself?
Because if you're in a finite group, then the subgroup will also be finite, right?
So it's a modular addition.
You mean finite field?
Yeah. I mean, I said if it's finite, right? It's always cyclic, because we define that cyclic just means that I can generate a group from one element, right?
Mm-hmm.
That makes it cyclic, even if it's infinite. But if it's finite, right? I mean, it really depends on what G is, I think.
G must be finite for A to be finite. G must be finite for A to be finite, right?
Not necessarily. I mean, I can at least give you like an extreme example, right?
Mm-hmm.
So take for example Z, and then does anyone have, like, it's really a stupid example, it's a trivial example.
Well, 0?
0.
0, yes.
Right. So 0 is finite, Z.
Mm-hmm.
But that's a trivial
Yeah.
example, but just, I don't know.
Maybe that.
It requires proof. Okay, proving, and I don't have don't necessarily have like a proof offhand. Okay. Now let's look now again at congruence. Okay, at the modulo, like we did, but we'll define it a little bit differently. So we'll say that age is a subgroup of G. Remember, that's how we defined the subgroup. And then we'll define a relation, okay? We'll call it right congruence, okay? And the relation will be defined as AB, right? Such that, too many, the relation will be AB, such that A equals B plus H. Okay, we can say B times H, right? Whatever. You understand. Plus is just easier here. Just easier to understand. So A equals B plus H with H in H. Okay? So if we define this relation, this is typically called the right congruence, okay? Oh, sorry, the left congruence, because we're on the left of H, okay? And then if we now define equivalence classes, right? So right, let's define the class A. I remind you, right, is basically it's equal all B belonging to G, such that AB belong to RH. Okay, so we're keeping A constant, and then it's all the B's that obey these, right? Okay. So what's the size of A? Right, if we look just at this class, how many, this is an equivalence class, right? So what's the size of the equivalence class? It's H, right? Right. So the size of the equivalence class is H, and we call all of these cosets of H, okay? So actually, if we think about it, right, I think that we could write, and this is probably not such a bad abuse of notation, but we could write that 0 is H. Okay? And then all the rest of them are, so 0 is a group, right? Because H is a subgroup. What?
Why is it H?
Hmm?
Can't there be more than one B for any H and H?
Maybe equal is whatever, I mean, with the minus and stuff, but it's generally speaking, I mean, this would be a group, okay? This would be the only, out of all of these, this is the only one that would be a group, right? Because we need the 0. Okay, this creates a partition of G, right?
That's modulo, no?
Where?
The operation, the relation.
It doesn't need to be modular.
Okay.
It's basically, you're saying that A and B are a pair that always has this relation. Okay? Now if H, whatever, I mean, let's just, to make it easy, just think of H as finite. Okay? So if H is finite, okay, then when I look at any class, it would be the size of H, right? Because for each H in...
assuming there's a single B.
For each H in here, there will be a B.
Yes.
Okay? Now, so this set, right, this equivalence class, which is a set, right, would be the size of H.
Yeah.
Now the equivalence class that includes, and these equivalence classes are a partition of G, so they don't have any overlap. So the only one that can be a group is the one that has the 0 element, right, or the unity, the identity, sorry, element. In order to be a group, you need to have an identity. So 0 is the only one that can be a group. None of the others.
0 can be in
when I set A 0, okay?
No, but if ZA is not 0, B can still be 0. You define it as any B in G.
Yeah.
So B can still be 0, and then it's fine.
No. Okay, so if A equals 0, right? B will be 0 when H is 0, right?
Okay. But if A is not 0, B can still be 0.
Maybe we're not. No, it can't. But let's think about it. But it's not possible that 0 will be in more than 1. Okay, just because it's a partition.
Yeah.
But let me think about it. Okay, you think about it at the same time as well, and we'll resolve it a little bit later, because I think it's just confusion. I don't think that it's yeah. So if this is 1, for example, right? Let's just imagine that H is, say, right, like if we put, say, N here, right? Don't forget, okay, I'll tell you why. It comes from the fact that H has to be, I mean, it requires proof in the general case, but it can't happen if H is a group. Okay? If H is not a group, then it's different. But if H is a group, then it cannot happen that I'll have 0 in more than sorry. If H is a group, then 0 has to be in the 0 group. But let me think about it offline. I'll give you like a concrete example, maybe in the next session. Okay. All right. Where were we? So we said that all of these, right, the size of an equivalence class is the size of H. Okay. And then we call the number of equivalence classes. Okay, so we can talk about how many equivalence classes are there, right? And that actually, we mark it like this, and this is called the index of H in G. Okay, so the number of equivalence classes is equal to the size of G divided by the size of H. Okay? And this makes sense because if all of these are size H, right, then we prove that they partition the space, right, because they're equivalence classes. They partition G, so if they're all size H and they're unique and they partition G, then the number of such classes is always the size of G divided by the size of H, and actually this is more general because what it says is that no matter what, the size of any subgroup divides the size of the group. Okay? When we say divides the size of the group, it means that it divides it without remainder. Okay? And that's a general result. And this is called index. Okay? This is good to remember. This is called index of H in G, and this is called we said before, order. So when we take the product of the order of H times the index of H in G, we'll get the size of G.
Is it also called cofactor, or is that something else?
I don't know that terminology of cofactor. Not for this, anyway. Okay.
So
But these are called cosets. Okay. So if 0 is, I mean, this is important. If 0 is a group or a subgroup of G, the cosets are not. Okay. Primarily because they're like offsets of these, and they don't have the identity element, at least that. Then we can show that they don't obey the addition, they don't have closure, they don't have many things. So they're called cosets, okay? And we'll see that a lot, okay? So the group of cosets, which is a group of group, is a group on its own with a special addition. But the cosets themselves are not necessarily groups or subgroups.
So the index of H in G is the number of cosets, or
Number of cosets, exactly. Yeah. We can also say that it's the number of cosets of, cosets of H in G.
generated by the current relation.
Exactly. Yeah, exactly. Okay. So now let's get into some maybe important properties of subgroups. Okay. So these are all like theorems of subgroups, and we're going to actually I've got 5 theorems here that are important, and we're going to prove them all. And I think that we'll try and also provide examples, okay? Or at least one leading example, I think, that could cover all of it. So let's start, and then I think we'll introduce the example after we get through a few of these. So the first theorem says the following. It says that every subgroup S, okay, of the cyclic group G, okay, I'll skip group, is cyclic. Okay. So if I've got G that is cyclic, all its subsets are cyclic. Okay. So take this the trivial subset, right? If we define S equals E, then obviously that's cyclic, right? E or 0.
What is E?
The identity element, always. Okay, so I've got a subgroup. We can even say that, right? We generate a group with E as a generator, with the identity as a generator, right? So a group consists of itself. It is a trivial group, but it's cyclic. Yeah. We actually used that group before, right? 0. It's the same one. Okay, now let's take a different one. So this is like maybe case A. Okay, case B is more complicated. So let's assume that G is defined as follows. Because it's cyclic, I can do that, right? I can say it's got a generator A that generates G. And let's choose A to the power of K, right? Which belongs to G, obviously. Let's choose A to the power of K that belongs to S, okay? But we choose it where actually K is is minimal. Okay? We choose the element of S, okay? S is like, right? S would be, I don't know, a to the power of the K1, a to the power of K2, whatever. A to the power of K, I don't know, N, okay? We choose the element where the K is minimal. Okay? Right. Now, what can we say about this? We can say that if we take this element and we generate some subgroup of G, okay? We can't say that this equals S, but we can definitely say that it is in S, right? Just because of group axioms or properties.
What do you mean by K is minimal?
I mean all the elements of S are powers of A, right? Because
S is the set of G. Yeah.
Right, because S is a subgroup of G, right?
Okay.
So you can define all the elements in S as powers of K. So I want you to go through all the elements and find the one where K is minimal.
Okay.
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 Not A to the power of K. K. Okay. And then if I generate a cyclic group based on A to the power of K, then it's definitely, it's at least a subgroup of S. Okay. Now, I want to convince you that what I'm going to try and do is convince you that A to the power of K actually equals S. And if I convince you of that, then obviously, I mean, it's even more than I need to do, but obviously S is cyclic. Okay. So how do we do that? We now choose, let's just, I can use the board, we'll just write it in short, K minimal. Okay. And we mean minimal positive, right? Not minus or anything like that. Okay, so now what we're going to do is we're going to choose another A to the power N. N is different to K, or I mean, not necessarily, but whatever, just any number, such that A to the power N belongs to S. Okay, so choose. Yeah? Choose another element, a general element. Now, by definition, right, we know that N equals Q times K plus R, with R less than K. Okay? We can always take two numbers, N and K, right, and define it in that way. It's just the division of K by N, right? So for example, if N is smaller than K, then Q is 0 and R equals N, okay? Now if we do that, then we can say the following. We can say that A to the power N, I'm going to already break it up, okay? What does it equal? It equals A to the power of K, all of that to the power of Q, and all of that times A to the power I. Right? And just look and make sure that I haven't made a mistake. Okay. What does this mean? We know that this, right? This belongs to S because it's just the power because of this, right? Right? Because if all powers of AK belong to S, then this belongs to S. Right? And because of closure, right? This belongs to S, this belongs to S, then this means that AI also must belong to S. Right?
Why?
Okay. if I've got A to, if this belongs to S and this belongs to S, right? Then if I take this and multiply it by something, right? Just because of closure, it needs to belong to S.
The multiplication is actually the addition.
Yeah, the addition. We're basically looking at the multiplication as
closure works a different way.
what?
Closure means you take two elements in a group,
Yeah.
you add them, and you get an element in a group.
So we're now multiplying. Okay, multiplication
No,
is
fine.
our operation.
I'm multiplying,
Mhm.
whatever you want to call it.
Mm-hmm.
But closure doesn't mean that if you take an element, multiply it with an element outside the group, you will get something outside the group.
You need to
It's
say.
not-
No, but A as the.
AR belongs to G.
AR belongs to G, yes. Okay.
From closure, it has to belong to S.
To G.
But, AKQ, you can have the
Inverse, yeah.
inverse
Yeah,
Yeah.
it's because you have the inverse of AKQ.
because it's in S, and then you get that AR is the.
And then you get what you want.
Yeah.
Like I can always move this from here
okay.
to
Because
Because
it's in
Those are
S.
plus inverse.
Yeah.
Yeah.
that's a good comment. Yeah. So I can move, right? I can move this to here,
With the
and then I
inverse.
get a multiplication of two elements in S.
Yeah, so you need another stage.
So this has to be, right?
Mhm.
Okay. So if this is true, right? Then one of two things. Either from this, either R is 0, and then it's trivially with A, right? Because A to the power of R to the power of 0 will just be E or 1. It's fine, right? Or not. But if it's not, then R is less than K, but when we started, we said that K is minimal. Right? That's how we build this.
Mm.
Right? So it can't be. Otherwise we have a contradiction with our construction.
So there are no other.
So that means that R has to always be 0. Okay? And if R is 0, then that means that, right, this leads to,
N belongs to.
because R is 0, that S is actually equal to A to the power of K, to the group generated by A to the power of K. Okay? And notice that this is not, it's not a trick, it's because I chose K minimal, right? If I would have chosen K not minimal, then this may not have happened, okay? This may not have happened that I would have generated the whole subgroup S.
Yes.
Now, a byproduct of this is that S is also cyclic, okay? All right. So, and remember this, just sort of like look at this and keep it in your mind, because this is going to be very similar to another proof that we're going to do. Okay, this method. Just erase this and new next theorem. Okay, theorem number 2. If we take a cyclic group, A, okay? We always, by the way, we'll interchange like A and G, right? G's will be our group, S will be our subgroup, and A will always generate G, okay? So, if we take a cyclic group generated by A, which will, we may not use G in this proof, but of size n, okay? Then, if we take any group generated by A to the power of K, meaning that we take any of these, any element in this group, and we generate a subgroup with it, right? then the size of this subgroup will equal M divided by the GCD of K and M. Okay, GCD, greatest common divisor, right? Okay. And you already know, you at least know an example because you know that if K and M are co-prime, right, then A to the power of K is just another generator of the same group. Right? That you should know from just prior knowledge. So how do we prove this? Okay. So let's define, just to make the writing easier, define D as the GCD of K and M. Okay. And then let's assume, okay, assume some n such that a to the power of kn equals e, or equals 1. Okay. Okay. We're basically just finding some n such that, right, n basically, and you know what we're going to say? We're going to say like before that n is minimal. Okay? So we're finding the first n such that a to the power of kn equals e. And n is what? What's n for this subgroup? N is the size, right? It's the order. It's the order of the subgroup. Because if I take the generator and I just times it with itself n times, and n is the minimal, right? Because it could be 2n, 3n, whatever. But if n is the minimal one that is with this, then n is also the order of the group, or of the subgroup, okay? Now, I can do the following. I can say that a to the power of kn is also equal to a to the power of m times L in, or whatever. It's actually in n.
Can you repeat the size?
Simply because if I take a generator and I generate a cyclic group, right? When do I have the whole group? When I go back to 1 or to the identity, right?
Oh.
So a to the k would be the first element, and then I go through.
Not when you go
when
back.
I go back.
Not when you go back to the generator.
Yeah, but that would be this. Yeah,
and plus 1.
It's true, but that would be the last one. When I get to when you get back to the generator, it's like an extra element, right?
Oh,
so when you get to 1, it's all the elements, right?
Doesn't it require proof? Like it's
That what?
like this is always the
This?
case.
No, we proved this. This has already been done. That's the definition of a generator.
You can generate everything.
Because the generator generates a group, right?
Yeah,
Or a
that's
subgroup.
No problem. Yeah, you can
So
get,
once you've gone back to 1 or to the generator, you're no longer generating any new elements, right? Forever.
Yeah, for sure.
So that's it.
Sure,
So that's the group.
you need to be in the group, but who said you go back to to this one? Like maybe it's like the order is
Because
like,
you can see
What do you
because you go
like
one.
maybe
one
I
into
finish all the elements in the group, and then I add it one more time or multiply one more time, and then I getting not to the identity,
But
to another.
No.
but you can prove it like this because see, you are smaller than n, and
Yeah.
you get all sorts of group elements, but you haven't yet got to e, right? So you still need to generate e. so you haven't generated all of them. Okay, then you generate E. So you generated E, but the next one that you generate is the generator itself. So you got to someone that you already generated.
I understand.
Okay.
If I understand your question, you're saying how can maybe I'll generate myself before I generate E. If you do that, you've got a problem because now you don't have the identity, right?
Yeah, you have
then it's not a group.
You have this connection always between the identity and the first.
And that's an axiom.
And the generator.
It's like we don't prove it. We
If
just
you got
accept
this
it.
you finish because the next one is generator and just repeating myself.
Yeah.
You can generate new now.
Now, just see if you believe this, right? So we're basically, what this is saying is that E equals E, okay, or 1 equals 1.
M times.
M is the order of the group. We're saying that, that E always has to be, because we know that a to the power of M is 1, right? Right? But basically this is saying that a to the power of kn is e to the power of some L. Okay? And E is, okay? It always has to be like that.
A to the M generates E.
Yeah, yeah. Okay. So this is nearly enough, okay? Because now we can say, right? Now we can say that the minimal n, right, or n mean whatever, right, has to be equal, right, to
ML divided by
huh?
ML divided by K.
Well, ml divided by k, yes, but or you know what? Let's do k n mean, okay, or the minimum nk. Let's make it like that. Okay, but we don't know n yet. Okay. So the minimum one, right? What would it be? It would be k times m divided by GCD of k and m. Now this requires just staring at for a bit. Okay. Why is this true? Okay. Why is this true? K obviously because k just has to be here. Okay. Now, in order for m to be in the final product, what am I allowed to divide it by? Okay, obviously km that obeys, but that's not necessarily the minimal. Okay, but I can divide m by some of its factors if those factors are also factors of k, because I only need those factor once. Okay, I don't need them twice. Okay, maybe I'll try and just write it more explicitly, but if I open k and m to like their prime factors, for example, okay, so I'll have we'll use p, okay, p k1 times pk2 times say pk3, okay, whatever, I mean I can obviously add like powers here as well, times say m, I don't know, L1 times m L2, okay, let's just say that this is like their breaking or whatever, right? So in order to have m, all I need is this and this, right? But just imagine that, let's say, this factor and this factor are the same, right? They just happen to be, I don't know, maybe it's 3, okay? Maybe this is 2 times 3 times 5, and this is 3 times 7. Okay? So 3 appears twice, right? So if I throw it away from here, right, I can still claim that k is here, right? So if I throw this, okay, this is k, right? The multiplication is k. This would be n. And actually 3 times 7 is still in there. So it's fine, right? So L would be, right? So 2 times 5 would be L, and 3 times 7 would be N. Okay. And now I'll just give you a few seconds to think about it, but
I mean, that is fine, but you're saying that.
so the dividing by the GCD just basically just gets rid of redundant factors that are there twice.
But what you're saying is that the minimum L is K divided by the GCD.
The minimum N.
Minimum
You're doing, yeah, fine. But I'm not looking for the minimum L. I'm looking for the minimum N. Right. If you find the minimum L, you'll also find the minimum K. It's the same. It's just a different partition of the vectors.
Because you're saying M has to be there.
Because M has to be there, yes. Otherwise, you will not get to E if M is not there. By definition, right? Of the group.
Okay.
Okay? O M. Okay. All right. So, I mean, there are other ways to prove this, but I think that this is the simplest one. Right? Because this, you actually, it's just by trivial construction. Right? There's nothing to it. You don't need to use any fancy like remainder type theorems. Okay. Let's see. How are we on time? 11:30. Nearly. Okay. So I think let's do. I do want to finish the theorems. I think that will take about half an hour, and then I think we'll stop there and we'll continue the next session. Do you guys need a break or we good to go? It's very quiet today, but it's less people, so.
What's the time now?
11:30. Okay. We can do a 2-minute break. No. Okay. Next. Okay. So 3. If D divides M, okay, this is the notation for divides. It means that D divides M with no remainder. Okay, and D is that GCD that we used before. Okay. Then A contains 1. 1 is not the unit, the identity, okay? 1 is like a single subgroup, okay? Of size D, okay? Just see that you understand what this means. So if we've got, you remember that the size here, right? We assume that the size of A equals M. Okay. We've got a group whose size in M is M, and we've got a divisor of M. Okay. Then there is just one subgroup whose size is D. Okay. I can generate it in many ways. I can get it like different permutations of it, but it's essentially the same subgroup, right? Because the group, I don't care about the order of elements, right? So how do I prove this? Any ideas?
Start by generating this.
Generating what?
This subgroup, right?
Okay.
Try to generate a subgroup.
So what's the trivial subgroup? Yes? How can I'll even make it more. What's the trivial generator
You need to
of
do
S? Right, it's all cyclic, right? Cyclic subgroup.
Yes, identity.
No.
A in power.
No, the identity, the size is 1.
A to the power.
A to the
size
power.
t.
A to the power m divided by
Exactly. Okay?
divided
So
by
a
d.
to the power of m over
M
d.
divided by d. Yeah.
Right? So we definitely know that this is one of the generators of S. Right? That's a trivial one. Now,
Now we need to show that.
let's assume, okay, that that we've got another group, okay? So the size of this group is D, okay? Let's now assume that we've got another subgroup, right, whatever, we can call it a stack, but we don't have to. Assume that A is also size D, okay? A to the power of K, with some K, okay? And then we need to show that AK actually equals A, that this and these are the same, right?
Okay.
Okay. So you can see already how this will somehow relate to the first.
So if you take A to the KB, right?
Yeah. You're right. Okay.
Have to be
A to the
cyclic,
KB
so-
is equals A to the M.
Okay.
And then you need to use D divides M.
You can go in that way. I think it's the same as what I did. This actually took me a bit of time yesterday, but I think I arrived at the punchline a bit quicker without doing that. Okay, but I think it's very similar to what you're saying. But let's start going through my proof. This is actually, by the way, one of the homework exercises, so you don't need to do this one. Or you can do it and see if you remember, or if you find another way to prove it. Okay, so what I did is I actually first of all defined R, right? That is less than M over D, okay? Such that K that I chose, okay, equals Q M over D plus R. Okay, again, I'm doing the same breakup. I'm just using I'm basically like looking at the relation between M over D and K. Okay. And this means, right, if I basically just multiply everything by D, right, what will I get? I'll get the D times K. And I think that this is where it meets somewhat what you were saying, right, is equal to Q times M plus D times R.
So you need to show that R is 0 again.
So, exactly. But why do I need to show it? I know that D times K, right? What do I know? Q times M, M divides Q times M, right? Really. But M also divides what? That's like your proof. That's to divide D times K, right? Because that's the order of the group.
M divides. Ah, okay.
it's the order of the group, so it has to divide it, right? That's from the previous proof, right? So we'll just write it. So we know this, right? And we know obviously that it divides this. And so, right, this means that when we do this, right, because this m divides this and m divides this, obviously m has to divide that, right? Otherwise there's no equality, right? So need to show that m divides dr, right? That's a problem, right? Why is that a problem? Because
dr is smaller than m.
r is less than m times d, right? So there's no number smaller than n times d where this will be true, right? Apart from 0. Right? So this means that r has to be 0. Okay? And if r has to be 0, right, we can go back and just say that from here, right, that k equals q times md, right, and we can already see that we're generating the same.
Why m divides dk?
Huh?
Why m divides dk?
That's because of our assumption that k generates a group of size d. Right?
Okay.
If you generate a group of size d, then your generator to the power d equals 1. Or right.
Yeah.
Okay. Great. So then these two groups are the same group, and so there's only one group. Now, actually, you can do the same exact theorem, but instead of taking, you know what? Yeah, you can say that if D divides M, then also there is one group of size M over D. Okay, but that's obvious because we already showed that, like, right, if you have, because this would be the order and this would be the index, right, and their multiplication is M, remember? So we could do it, we could do a slightly like we can change the proof accordingly to actually show that there is another subgroup of size M over D, or we can trivial. I'm just not presenting it. I think it's a pretty trivial thing because we can always say, okay, if D divides M, then M over D divides M, right?
Yeah.
The same proof, right? So,
But actually, to finish the proof,
yes.
what we've showed here is that a to the k is generated by a to the md.
That?
That a to the k.
Yeah, but you require that the group size is D. Okay. If you choose K where the group size is not D, then, because you could choose a K for something smaller than D, but by the assumption, it's the same group. Okay?
But you didn't hear my question.
No. I assumed your question. But you already know me, so yeah. Okay. Go ahead.
You've shown that a to the k can be generated by a to the md.
Then it's the same group, right? The same subgroup.
No, so how did you show that? I mean, I see how you've shown that.
Oh, this?
You
How
found.
can we do this?
No, not that. We found the q such that k equals q times m divided by d. Meaning that ak is an element of the group S.
Yes.
But how does it follow now that all the other
That it
elements,
generates?
that all the other elements in AK are elements of S?
I understand. Okay, so you believe that this generates a subgroup. I've assumed that AK is the same size, and I've shown that AK itself is in here, but how can I, so you're basically asking the question, maybe this is S, and this is S tag, right? And this is A to the power of K, and it's just here, right? But you can show it for any AK. So it's not necessarily one. Look.
But for any AK, you get a different.
Yeah, no, but I can show it to you now for 2K, 3K, whatever. Like I can show you that they're all in there. Right.
Ah, okay.
And then you'll get to. Eventually, you'll cover the whole thing. That's the same proof. Right? Okay. But good question. And I did miss the subtlety. Okay. Next. It gets easier. Actually, the fifth one is really, it's less of a theorem, it's more like a corollary. So we really only need to do one more proof. And actually, the last proof, we're going to also do an example. So we'll show it through an example, and I think that you'll see some of the other theorems that we did through that example. A simple example, but very important one. I'm just going to introduce, and I mean, this is worth doing like a whole session about, but there's a function that we mark with, what do they call these? Psi or phi?
Phi.
Okay. I always get confused. So, phi of f is actually Euler's totient function. Okay. What does it count? So it actually counts and assume that f is a positive integer. All right. It will count from the group of all the integers, all the positive integers smaller than f, okay? It will count how many of these are coprime to f, okay? The definition of coprime means that the GCD is 1, okay? They've got no shared factors, okay? I mean, f and the coprimes don't need to be prime. Okay, it's important to understand. They just need to not share any prime factors with one another. So we're going to use this. We're not going to introduce it, or not more than I just did. We're just going to use it as a like a black box for the next theorem. So the next theorem says the following. It says that that let f divide m. M again is the size of the group A, right? Then we say that the cyclic group A contains phi f elements of order f, okay? It means that each one of the elements of these phi f elements, right, when I raise it to the power f, it will equal the identity, it will equal 1, okay? But it distinctly contains phi f elements, no more. Phi f distinct elements. Okay. So, how do we prove this? We prove it as well. It's actually
of order f?
Of order f. An element of order f, if I take, say, b, if the order is f, b to the power f equals e, and f is minimal. Okay. That's what it means that I've got an element of order F.
So it contains Phi F
Elements, yeah, the group generated by A contains
contains Phi F elements of
You're missing, no, you're just missing that. I mean, I said it, but I didn't write it. The size of A is M.
Okay.
Size of A is M, okay? And I've got a divisor of M. Then within the group generated by A, there are F elements, Phi F elements of order F.
Okay.
Okay? All right. So let's see. So we start off, okay, I'm just going to copy it to here. We say that the size of A is M, okay, by definition. And we can also say, we can define that M equals D times F. Okay, we can define it because F divides M. Okay, so I just say that D is the result, or the quotient, or whatever. Okay? Now I'll take A to the power of K, a subgroup. I'll define one. I'll find the K such that the size of this subgroup is F. Okay? If that's true, so A to the K is one of these elements that we're talking about. Okay? And we actually just want to count how many such K's there are. Okay? I know that if this is true, right, by a previous theorem that we did, right, I know that F, the size here, is equal to M divided by the GCD, right, of K and M. Right? This we saw. You recall? I think that's the second theorem, right?
Yeah.
I think that's the second theorem, right? And if this is true, then just by the definition that we did here, we can just replace it and say that D, right, which is like the quotient of these two, is actually equal to the GCD of K and M. Okay? Right. Now just write M divided by D is F. Yes. Okay. So I'm just going to focus on this and just do a little bit of playing around with it. Nothing, nothing crazy. Right. I'm actually looking for how many K's satisfy. Got it like that. Yeah. Okay. How many K's satisfy this? Right. So I need to show you that it's PF K's. Okay. Unique K's. How do I do this? I will say that first of all, and by the way, right, such that K has to be greater than 0 and less than equal M, right? I'm not interested in K's that are larger than it, right? Because I'm looking at just the ones, the elements of this, right? So how do I do this? I take this and I divide everything by D, okay? So what do I get if I divide everything by D? And this is allowed to do with the GCD, and you can verify D over D, right? I'll just write it here so that, right? D over D is 1, right? GCD. Okay, K over D is whatever, something, and then M over D is F. Right? I just divided everything by D. Right, so I'm allowed to do it because then I remove vectors from here, so they're also removed from the GCD, right? Now, and also now, if here I had that K is between M and 0, so here K over D, which is some number, is between M divided by D, which is F, and 0. Right? So now let's replace K over D with, this is just a number, right? K over D. Okay? And then I ask how many of the numbers that are smaller than F, look at the question, right? How many numbers that are smaller than F are GCD 1 with F? So how many?
5.
5, right? By definition. Okay.
Okay. So you found 5 subgroups, right?
So there are 5 subgroups of order F. Yes. It's equivalent.
Yeah, but there are
to
much
this.
more elements.
Huh?
But each of those subgroups has F elements.
F elements, right? So they're
So
order F.
actually you have F times Pf.
By the way, it's not true. No. You don't have phi F groups of order F because you've got one. It's actually one subgroup of order F, but it's got phi F generators. Okay. We proved before that there is only one subgroup of order F because they're both cyclic. Okay.
Okay, so you have
Phi F generators for that group of order F. That would be like a different way to say it.
Don't you get K over D equals phi F? So K is...
Not K over D equals 5, but how many K over Ds are there that give 1?
So we have phi F, K over D.
No. Why? K over D, just replace it with a number.
Oh.
Okay. This is just a... I'm asking the question now. How many ages are there that satisfy this?
Oh, okay.
And that's the question. Okay?
They will all generate the same group.
Okay.
That's the previous
one,
right?
So you can take
So we're not
any one
going to
of
prove it
them.
again, huh?
You can
take any
one of them. You
Yeah,
get the same
and we're
group.
going to show it with an example. And actually the next, before we go to the example, I'll just do the next theorem, which is very related, and you already said it. And we're going to say that, right? The group A of size M, right, has how many generators? 5.
Yes.
5 M generators. It's the same, right? It's just a corollary, really, of this theorem. That's fine. Okay? Now, let's just stop and do an example, and then that's it for today, because it is getting late, and I can see that you're tired. So
From this follows that if M is prime, then every element
exactly.
is a generator.
Yeah. So it's actually a useful theorem and corollary. Okay. Like everything else that we're doing here. Okay. We're tired. All right. Kartik here. Some Okay, so let's take the following group, which you know well, okay? So G, okay, we'll take the numbers 1, 2, 3, 4, 5, 6. And we'll take the operation plus mod 7, right? And we know that that's a group, okay? Multiplicative group. And now let's just generate all the subgroups.
Zero.
No, because it's,
Zero.
oh, sorry, plus, you're right. But
Okay.
multiplication
Oh,
modes.
okay.
Okay, sorry, sorry. I just want to, I mean, with the plus, it's a little bit boring. Okay. Okay. So now let's generate subgroups. Okay. So we'll do like this order of the subgroup and then subgroup, and we'll generate all the different subgroups. Okay. So we start with the subgroup 1 or E, right? But here is 1, right? The order is 1. Yes. The second one. So we've got 2. 2 times 2 is 4. 4 times 2 is 8, which is 1. Modulo 7. Subgroup of order 3. Okay? We're going to do it quickly, and then you could verify. 3 times 3 is 9, so it's 2. 2 times 3 is 6. Okay? 6 times 3. The generator is always the first one. Okay? 6 times 3 is 4. 4 times 3 is 5. 5 times 3 is 1. Good. So we've got our whole group, right? So the order is 6. So this is a subgroup that contains the whole group. Next one, 4. 4 times 4 is 1. 4 times 4
is 2.
2.
Sorry. You're right. Of course.
2 times 4
2 times 4 is 1. Yeah, no, you're right.
Yeah, I think
It has to be, right?
yeah, you can.
Because of the theorem that we already did, that these are the same groups. My apologies. I got a mistake in my notes. But it was late. Okay. And I was actually just looking for the 2 big groups. Those are the ones that interested me. 5 times 5 is 4. 4 times 4, we can already, 4 times 5, 20 is 6. 6 times 5 is 2, right? 30, 28. 2 times 5 is 3, and 3 times 5 is again 1. Okay. By the way, I think that because there are only 2, you can see that these are exactly like the order is just inversions, right? Which makes sense, right? They're all inverses. Like if you look at 3 and 5, 2 and 4, 6 and 6. Okay. This one is of size 6, and then finally the last one, 6. Okay. 6 times 6 is 1. We saw this already, right? So the size is 2. And you can see here that, you can see a few things. You can see that there are really, for example, like, right, phi of 6 equals, you can see it from here, it's got to be 2, right? But you can calculate it, right?
Yes.
So phi of 6 is 2, and that's why you get 2, and they're the same, right? You get 2 from 3, they're the same, and then 1 from 1 and 1 from 2.
And all the orders divide the original order.
Exactly. Okay. Any more questions? Okay. So, see you next time.
Thank you.
Done.
Done.